Welcome to Programming in Python. In this first lecture, we won't write a single line of code. Instead, we'll build the mental framework you need. We'll answer, what are we actually doing when we program? And why is Python the right tool for this? Here's our path. We'll start with the nature of computation itself, what a computer fundamentally does. We'll then define algorithms and see how they are executed inside a machine. This leads us to the core of the lecture. Understanding programming languages, their rules and potential errors. We'll clarify a key distinction between scripting and programming languages, which explains Python's unique position. Finally, we'll cover installation and a preview of Python's building blocks. At its core, a computer is a machine for processing information. It does two things with incredible speed. It performs calculations, billions per second, and it remembers results. But crucially, it possesses no inherent intelligence. It only knows the very specific primitive operations built into its hardware and the sequences you, the programmer, provide. Your job is to assemble these primitives into meaningful recipes. This is the difference between knowing what and knowing how. Declarative knowledge is a fact. The square root of x is y, where y equal x. Imperative knowledge is the recipe to find y. Like Newton's method shown here, start with a guess, check it, improve it by averaging, and repeat. This recipe is actionable. It transforms a static fact into a dynamic process, a series of steps the computer can execute. This is our bridge from problem to program. That formal step-by-step recipe is an algorithm. It must have three things. First, a finite sequence of simple, unambiguous steps. Second, a flow of control. Some steps may repeat or branch. Third, a clear stopping condition. The square root method is a perfect algorithm. So programming is essentially the art of designing and expressing algorithms in a language a computer understands. How do we feed an algorithm to the machine? The revolutionary idea is the stored program computer. The algorithm itself is stored as data in memory. The CPU fetches instructions one by one. Do arithmetic, move data, perform a test. Tests are key. They allow the flow to change, creating decisions and loops. This fetch, decode, execute cycle is the heartbeat of all computation. Your laptop is a stored program computer. Its hardware can run any algorithm you load into it. Theoretically, only a handful of primitive operations are needed to compute anything. This is Turing completeness. Modern languages like Python offer a richer, more convenient set. A programming language provides these primitives, plus rules for combining them into expressions like 3 plus 5, 2, and defines the exact value and meaning of every valid expression. To write valid code, you must follow the language's rules at 3 levels. First, syntax, the grammar. High 5 is syntactically invalid Python, it's gibberish. 3.2 5 is valid syntax. Second, static semantics, rules about meaning that can be checked before running. 3 plus. High has valid syntax, but it's a static semantic error. Python's rules don't allow adding a number to a string that way. These first 2 layers are about the form of your code. If your code passes both, we reach semantics, the actual meaning, what happens when it runs. In programming, semantics are unambiguous, but they may not be what you intended. This leads to our 3 error categories. Syntactic errors, caught immediately. Static semantic errors, often cause clear runtime exceptions. And logical errors, the code runs but does the wrong thing, giving a wrong answer, crashing, or looping forever. These logical errors are your primary adversary as a programmer. Now, with this understanding of languages, let's tackle a common point of confusion. What is the difference between a programming language and a scripting language? Let's start with definitions. A programming language is a general set of instructions to achieve a specific output on a computer. It's a broad term. A scripting language is a type of programming language specifically designed for writing scripts. Short, often interpreted programs that automate tasks within a special runtime environment, like a web browser or an operating system shell. A key traditional difference is in interpretation. Classic programming languages like C are compiled. The entire source code is translated once into a standalone binary executable file. Scripting languages, like traditional JavaScript, are interpreted line by another program. For example, JavaScript code is embedded in HTML and interpreted by the web browser. There is no standalone .exe file for the script itself. This leads to a difference in memory and deployment. A compiled C program creates a binary .exe file that the operating system loads directly into memory and executes. A scripting language's code is typically just a text file. The host program, like the browser, loads this text file and interprets its commands. The script itself doesn't create a separate memory footprint as an executable. It runs within the host's process. Therefore, their design philosophies historically differed. General-purpose programming languages were designed for building full, complex, standalone software applications from the ground up. Scripting languages were designed for gluing together components, automating repetitive tasks, and making coding for a specific environment quicker and easier. This often meant that for a given task, scripting languages could achieve the result with fewer, more specific lines of code compared to a lower-level programming language, which might require more code to handle memory and system details. Historically, programming languages were categorized by generation, like 1GL, 2GL. Scripting languages were categorized by where they ran, server-side, like PHP on a web server, or client-side, like JavaScript in a browser. The conversion process also differed. Compilation is a one-shot translation, while traditional interpretation is line by line. Each approach has trade-offs. General-purpose compiled languages offer advantages like high speed of execution, direct hardware access, and fine-grained control. Their disadvantages include a steeper learning curve, longer development cycles, and generally being less memory efficient for quick automation tasks. You have to manage more details yourself. Traditional scripting languages offer the advantages of rapid development, easier learning, high portability, and dynamic features. Their main disadvantage was speed. Line-by-line interpretation is slower than executing native compiled code. They also traditionally had less control over low-level system resources. Let's look at this summary table. It contrasts traditional examples, C++, programming, versus JavaScript, scripting. C++ is compiled, runs independently, and is used for full-scale software. JavaScript is interpreted, runs inside a browser, and is used to automate web page behavior. This was the clear historical divide. But notice, where is Python in this table? This is the crucial point. Python is a hybrid that challenges this strict separation. And that brings us to why we use Python. Python takes the best from both worlds. It has the high-level, readable syntax and fast development cycle of a scripting language. You can write a few lines and see results immediately, but it also has the power, structure, and extensive library ecosystem of a full-fledged general-purpose programming language. It is object-oriented, free, portable, and incredibly versatile. It's interpreted for ease of use, but its code is compiled to efficient bytecode. This dual nature makes it the perfect language for learning. You grasp concepts quickly, and for professional use, as it scales from simple scripts to massive systems like Instagram or YouTube. So let's get it installed. The process is straightforward. Visit the official website, python.org. Go to the download section and get the installer for your operating system, Windows, macOS, or Linux. Running this installer will give you the core Python interpreter and a basic integrated development environment called idle, which is sufficient to start. Understanding how Python runs code demystifies its hybrid nature. When you execute a Python program, it goes through two phases. First, your source code, the .py file, is compiled into an intermediate, platform-independent format called bytecode. This happens automatically and is cached in PYC files. Second, this bytecode is fed into the Python virtual machine, PVM, which is the runtime engine that interprets and executes the bytecode instructions. So Python is both compiled and interpreted. You can interact with this system in two primary modes. The first is interactive mode. You open a terminal, type Python or Python 3, and you are presented with the prompt. Here you type a statement, press enter, and see the result immediately. It's a conversation. Typing 2 plus 2 gives you 4 right away. It's an invaluable tool for experimentation. The second mode is script mode. This is for writing real programs. You write your code in a text file, save it with a .py extension like hello.py, and then execute the entire file from the terminal with Python hello.p. The interpreter reads the file, compiles it to bytecode, and the PVM runs it from start to finish. We will use both modes extensively. Looking ahead, all programs are built from a set of fundamental constructs. These are the universal building blocks of programs. You will get data from the outside world, input. You will display results, output. You will execute statements one after another, sequential execution. You will check conditions and choose different paths, conditional execution. You will repeat actions, repeated execution. And you will package code into reusable units, reuse. These blocks manipulate data, and in Python, every piece of data has a type like integer or text string, which defines its properties and what you can do with it. For example, you have numeric types like integers, int, and floating point numbers, float. You can perform operations on them: addition, plus, subtraction, multiplication, true division, which always gives a float, integer division, remainder, percent, and exponentiation, add. These operations follow specific rules of precedence. Like in math, exponentiation happens before multiplication, which happens before addition. You use parentheses to control this order explicitly. Finally, as you write code, you must document your thinking. You do this with comments. A single-line comment starts with a hash symbol, #. Everything after # on that line is ignored by Python. For multi-line comments, you enclose text in triple quotes. Comments are not for the computer. They are for your future self and other programmers, explaining the why behind the what. To summarize, programming is the art of formulating imperative knowledge, algorithms, and expressing them unambiguously in a formal language. Python is a language that makes this art accessible without sacrificing power. It sits at the powerful intersection of scripting ease and programming depth. Your task now is to install Python, open the interactive shell, type a few expressions, and get a feel for the conversation. In our next lecture, we will dive into that conversation, learning to use variables, understand data types deeply, and write our first complete scripts. I'll see you then.